Good evening to all the students. We will start in few
Good evening,
minutes.
ma'am. Can you hear me?
Ha. Yes, Swapna.
Hello?
Yes, your voice is clear, Swapna madam.
Hello?
Hello, Swapna madam. Am I audible? Hello, Swapna madam.
మేడం వినిపిస్తుందా? నేను ఆన్లోనే ఉన్నా. Ma'am, can you hear me now?
Yes, your voice is clear. Dear students, please quickly ask your others also join immediately. Already we are late by 8 minutes. So we'll start in 2 minutes. Sahasra, please put a message in the group. Ask them to join immediately.
All? Can you hear me? Sujata ma'am?
Swapna.
Yes, okay.
Okay.
Ma'am, can we start?
Yeah, we'll start. Sahasra,
Yes, ma'am.
first introduce the resource person.
Yeah. Uh,
We'll
welcome
start.
everyone. Welcome everyone. Today our resource person is Dr. T. Swapna ma'am. It's my great privilege to introduce ma'am, an accomplished academician and or researcher in the fields of electronics and also communication engineering. She gained her PhD in microwave engineering from JNTU Hyderabad and has over a decade of dedicated
Just a
teaching
minute.
and
Sahasra, just a minute.
yeah, ma'am.
Sahasra, madam will continue.
Yeah, okay.
Yeah, good evening all. I am Dr. T. Swapna from EC department. I'm working as an associate professor since long from 2006. I completed my PhD in wireless communication, 5G wireless communication from KLU Vijayawada. So in 2022, I completed my MTech in embedded systems and BTech in EC department. So here I am going to present today's presentation. The topic of my presentation is the OFDM wireless communication using OFDM in MIMO systems. Okay, so overall we are going to see how to design a MIMO using a OFDM. So first I will share my slides. Step by step we'll go through it, starting from single antenna towards MIMO. So I hope it will be a good lecture for you. So I am going to share my slides. Just a minute. So first of all, I want to thank to Sujata ma'am, HOD sir, Dr. SPV Subbarao sir, and our college management to give me the chance of giving a lecture in this workshop. Just a minute, I am getting some difficulty in sharing the screen. Once
Okay.
again, I'm trying. Now, is it visible? Is it audible? Hello?
Slides are visible. Voice is also clear.
Yeah. Okay, ma'am. Thank you. Okay. So now before going to start, I want to tell that today we are going to see the implementation of MIMO OFDM. Actually, we are going to see MIMO OFDM using MATLAB, but we'll start with SISO, that is a single input, single output antenna. Once it is very clear to you, then it can be implemented for any MIMO. MIMO means multiple input, multiple output. In 4G and 5G systems, we are using a MIMO antennas at the transmitter and receiver. So though in 4G systems, MIMO the size of MIMO is max 2 by 2 cross 2 or 4. But when we go for implementing 5G communications, we'll go for massive MIMO, so many large number of antennas, so many antennas at the transmitter side. So first we'll see a simple single input, single output OFDM implementation with a QA modulation using MATLAB, and then it will be easy for you to understand how it works in MIMO. So these are the two things we are going to see in this presentation. So here, first I will give the introduction to what is OFDM. Now, initially, when we started, when the wireless communication started in 1G, 2G, in 1G we had used the multiplexing techniques as a FDM, frequency division multiplexing, where, as we know, mostly all the students know, as we studies this FDM, TDM in our basic analog and digital communication. So in FDM, the whole frequency band was divided into sub bands, and in that sub band, one carrier is given for one person, like that. So that was your FDM, frequency division multiplexing. Then in 2G, we switched to TDMA, time division multiple access, where the time slot is allotted to each user instead of giving the frequency slot. So it was used to simply increase the channel capacity as well as the number of users. Then in 3G system, we we accepted the term CDMA, code division multiple access, where a unique code was given to the user. So that was the CDMA technology we had used in 3G, third generation communication system. While in 4G, we are using OFDM, orthogonal frequency division multiple access, and in future also we are going to use the same. So that's why OFDM is very important for our communication people, in which we everywhere we are going to use the OFDM in our 4G and 5G wireless communication system. So orthogonal frequency division multiplexing, it is somewhat similar to your FDM, which we had used in so long back in 1G. But one slight change is that OFDM, that is orthogonal, all the frequencies which we are using in this FDM are orthogonal to each other. Okay, so just you can see this diagram. This is a FDM and second is a OFDM. So in FDM, as we know, whole frequency channel we are dividing into sub channels, while in OFDM, same the carriers we are using which are orthogonal to each other. Here you can see the peak of each frequency is corresponding to the zero of another frequency. So in this way they are orthogonal. So what is the main advantage of OFDM? That is a saving bandwidth. See, lot of bandwidth we can save, and this bandwidth you can utilize for other purpose. So that is the advantage of OFDM, and that's why we are going to implement this OFDM in 4G, 5G, Wi-Fi, and digital broadcasting. So the advantage of OFDM is giving the high spectral efficiency. So hence we are going to see the OFDM. So in OFDM, so main concept is what? Here we are splitting the whole data rate stream into many lower data rate streams. So we have a high data rate stream, the data is given or generated at a very high rate. So instead of sending whole data at a time, we are making into pieces, lower rate streams, and each stream we are transmitting on a separate subcarrier. That is the concept of your orthogonal frequency division multiplexing. So we are using subcarriers, so many subcarriers which are orthogonal to each other to conduct the lower rate streams. So that is the concept of your OFDM. So subcarriers are mathematically orthogonal, and why they are orthogonal? That they should not interfere with each other. So that is the use of the orthogonality. So what are the advantages of OFDM? It can handle multipath fading. So though this is one type of distortion, so multipath fading, as the signal transmits from one place to other with so many paths, we call it as a multipath. So uh, the whatever the distortions causes due to the multipath, it can be handled using OFDM. OFDM also helps in reducing the inter-symbol interference, and it will help in the efficient utilization of bandwidth. As we have seen, we'll save the bandwidth, we'll give the much more bandwidth in which we can that which we can use it efficiently. So this is the concept and the advantages of OFDM. Now this is a block diagram of a single input, single output orthogonal frequency division multiple modulator diagram. So this is very important. Now first, input data, as we know, we have the digital data. First we need a digital modulation technique. So as we know that the digital communication systems, first initially the data, then analog to digital converter, then source encoder, channel. So in this, so before modulation, our data is available in the binary form. Okay, and then we are using the modulation. Now here you can choose any type of modulation. We have different modulation technique, digital modulation techniques, that is PSK, QPSK, QAM, MSK. So many different types of modulation techniques are available. So generally QAM, QPSK we are preferring. These are helpful to send the large amount of data or large number of bits carried using the symbols. So we are going to choose some particular type of modulation. After modulation, now as what is the concept of OFDM? That a high stream data is converted into several low streams data. For that we need a serial to parallel converter. So the serial to parallel converter, so all the symbols coming from modulation are converted into parallelly, and then we are performing IFFT, inverse fast Fourier transform. So this is very important concept in OFDM modulator. We are using a IFFT to convert into this time domain, and then we are adding a cyclic prefix. Cyclic prefix is used to reduce the inter-symbol interference. So we need to add the cyclic prefix, and then again all the parallel data we are converting into serial and then transmitting through a channel. The same reverse process we are doing in the OFDM demodulator. So from the channel it is serial to parallel conversion, then we are removing the cyclic prefix. Simply this cyclic prefix is used to remove the ISI, inter-symbol interference. Then again, we are converting back into the symbols using fast Fourier transform. And again, we are converting parallel to serial conversion. Then we have to demodulate. So whatever the modulation technique we are using, corresponding demodulation technique we are using at the demodulator, and we are getting. So this is a complete OFDM block diagram for a single input, single output. So here transmitter is single and the receiver antenna is also single, and similar thing will be there in MIMO. You will get it. Now here, instead of going in theoretical detail, we are going to implement this block diagram using MATLAB. So we will see step by step how to write the program, what to declare, how to write the program, what are the things we need to do, all the operations, whatever described in this OFDM block diagram. Okay, so what is our process? First, the input data, we are doing modulation. So we are using here QAM. Now, you know about what is QAM. QAM is a quadrature amplitude modulation. It is a combination of ASK and PSK. You know ASK, amplitude shift keying, different amplitudes for different data bits, and the phase shift keying. So combining these two, amplitude shift keying and phase shift keying, we have the new modulation technique, that is a quadrature amplitude modulation. Now depending on the number, so there are different order QAM, such as 16 QAM, 64 QAM, 256 QAM. These are the higher versions used to transmit large number of bits at a time. If I consider 16 QAM, it will conduct 4 bits per symbol. 64 QAM, it will conduct 6 bits per symbol. So we can see the constellation diagram. The constellation diagram gives the position of these 16 or these symbols, 4 symbols or 16 symbols in 16 QAM or 64 QAM respectively. So we are going to use here QAM, quadrature amplitude modulation. So first the input data, we are doing modulation. Then as we know, we are converting serial to parallel. Means here serial to parallel conversion means what we are doing, we are using large number of subcarriers. So we need large number of subcarriers. So symbols are assigned to the subcarriers. Then we are performing IFFT. We are inserting cyclic prefix used to combat the multipart delay, and then it is transmitted over the channel. Here the channel which you are considering, it is a AWGN channel. AWGN, that is uh, Gaussian noise, additive white Gaussian noise channel. And then the same reverse process we are doing. So now we are going to implement this whole block diagram using the MATLAB. So we'll see one by one. Now see, first what we have to do, first we need to set, see, once again just go through the modulator block diagram. First modulation, then serial to parallel conversion, then IFFT, then cyclic prefix, then parallel to serial conversion, coming to channel, again the reverse process. So once you understand this block diagram, we are going to implement this block diagram using MATLAB. So first I will give the step-by-step process, what to do. I am dividing whole program into smaller parts so that it will be easy to understand. And then we'll run the whole program and we'll check the output. So first is the setting up the parameters. So first we are going to decide how many subcarriers we are using, what is the length of cyclic prefix, then what is the QAM order we are using, whether it is 16 QAM or 64 QAM, then number of symbols which you are going to transmit. So here I am considering 6400, you can consider anything. Then signal to noise ratio. Signal to noise ratio, here I am considering 20, it is in decibels. Okay, so first we are giving some parameters. You can do a slight change for these parameters we are going to implement. Then first, now before going to symbols, first we are to consider the binary data. Now we need a binary data in the zeros and ones. So for to generate the binary stream, we are using a randi function, randi, RANDI. So this we can say this function is used to generate the random integers between 0 and 1s. So we are generating random integers. But now how many random integers? It will be equal to number of symbols and log to the base 2 m. So what is m here? M is 16. So accordingly, we are generating the total number of bits. So each symbol, so in 16 QAM, for each symbol carries 4 bits, because 2 to the power 4 is equal to 16. So total number of bits will be equal to the number of symbols into 4. So here how many symbols are considered? 6400. So 6400 into 4, that many bits will be generated using this function. Okay, so random. So first we are generating the bits, and then on these bits and for all these symbols we are doing the QAM modulation. So here first we are converting, first we are converting the bits into the words or symbols. So for that we are using BI to DE, that is bits to D bits. So and so we are using a reshape function, so which is reshaping the total, the incoming into the number of symbols, and then we are converting into the convert them into the decibel. Then we are using the QAM modulation. So again, see, there are so many built-in functions available in MATLAB in our communication toolbox. So we are going to use this communication toolbox. So whatever the type of modulation, demodulation you want, you are going to use that particular toolbox or particular function. So here I am going to use the function QAM mod. So it is used for the QAM modulation. Now, on what you are doing the modulation? Data. What is the data? Data is in data in. I am storing in this data in variable. Then we have to give the order of the QAM. What is our order of the QAM? 16, which I have stored in M. Here M equal to 16. So here I am using 16, and we are considering by default unit average power. If that is average power, we are considering as a 1. So in this way, first we are getting the symbols. So we are using the QAM modulation. So once we got the QAM modulation, then we are converting in, then we are going to implement the OFDM. So as in OFDM, we are using large number of subcarriers. So whatever the serial data coming out of your modulator, we are we are dividing into parallel. So how many parallel? Equal to the number of subcarriers. So we are again using the reshape. So what the reshape will do? Reshape will convert this one dimensional data into multi-dimensional data, whatever we need. Now what is my new dimension of data? That is the number of symbols, that is the symbols that is equal to the subcarriers. Now we are using number of subcarriers equal to 64. So like that, first we are considering a symbol matrix. Now on this parallelly generated symbol matrix, we are doing IFFT. Now again, we have in MATLAB, we have the IFFT function. So we can do the IFFT function on which we are doing IFFT symbols matrix, and then number of subcarriers, that is the size of IFFT. We know IFFT, that is a 8-bit, 16-bit. So here it is a 64-bit. So we are doing a IFFT, and the output we are generating, we are storing into IFFT output. So we had applied the IFFT to convert the frequency domain subcarriers into the time domain subcarriers. Now for each subcarrier, we have to add the cyclic prefix. Okay, so what is the length of cyclic prefix we have considered? The length we have considered as 16. So we are adding that cyclic prefix into the stream. So then we got the transmitted signal ready. We are serializing again. So this parallel again we are converting into serial using this colon. So simply all the data will be converted into single dimension. Okay. So once this is now transmitted. So this is transmitted through a transmitting antenna, and it is given to a channel. Now here the channel we are considering as a AWGN channel, that is the additive white Gaussian noise. So in additive white Gaussian noise, so we are implementing a channel. So in this, I am using a channel function AWGN. See, all these built-in functions are available in communication toolbox. So we can use it directly. So received signal equal to AWGN. And what is going to AWGN? Transmitter signal. We have to give the signal to noise ratio. Okay, and then we get the received signal. So now so whatever the amount of noise we are adding through AWGN, it is depending on the SNR. If signal to noise ratio is more, less, we can say the noise is less, so accordingly you can choose the SNR value. Okay, so now we got the received signal. Now this is whole the transmission. Then we go to channel. Now from channel, again we have to do the OFDM demodulation. Okay, now in again OFDM demodulation, what is the process? First convert again serial to parallel, then remove the cyclic prefix, and then do the FFT. So the same thing again I am doing. Again I am converting serial to parallel using the reshape. Okay, then what is the what are the how many parallel? That is the number of subcarriers plus CP length. Then we are removing the subcarrier, and then we are carrying the FFT. Again, we are using the built-in function called as a FFT. Okay, so so we are removing the cyclic prefix and we are applying the FFT. and then we are doing the QAM demodulation. So again, we have the function QAM demod. It is used to demodulate the QAM signal. Again, on what we are doing this operation? The output of FFT. So all the things coming output of FFT, we are doing the QAM demodulation. Again, we are specifying the uh, the size. So here the QAM size is 16. We are giving the 16. And then again we are converting integers to the binary and then reshaping into the bitstream. So like that we are getting the received signal. Now after getting the received signal, we have to do some operation to check the efficiency of the system. So for that, we are calculating bit error rate. So what is the bit error rate? How many bits are there in error comparing the transmitted and received? So comparing the transmitted and received bits, we will calculate the bit error rate. So how to calculate? So we are calculating bit error rate simply using the sum of bits. We are calculating how many we are using not equal to. So how many bits are not equal to the transmitted bits, and dividing by total length of the bit. So like that we are calculating the bit error rate. So we'll calculate afterwards. We can visualize the constellation diagram of the 16 QAM by using the scatter plot. So we can see, we can use this scatter plot command or function we on the symbols to check what is the QAM constellation during transmitted signal and for the received signal. These are used to check the efficiency of our system. So this whole step by step whatever I have given, this whole program, okay, this once again, now this up to this whatever we have seen the program, this is for signal to noise ratio. Whatever we consider I think 20 dB. Now we can do whole program for 0 dB, 20 dB, 15 dB. So you can make it in a loop. Okay, so you can use a for loop, okay, where the signal to noise ratio can change from 0 to 20 like that. So here I had made the signal to noise ratio 0 to 5 and 0 with a distance of 5 up to 30, and the same operation I am doing, and simply I am plotting the bit error rate values for all this SNR. So this is simply a for loop 1 to 30 with a difference of 5. And here again I am calculating the same thing, received bits, transmitted bits, and bit error rate we are calculating, and then we are plotting the graph. So this whole program now I am going to execute. So this is a whole program whatever I had given in step by step. This I will forward to you. Afterwards you can copy this program. So I will show the execution of this. Can you see the program? Hello?
Yes, Swapna.
Okay, ma'am. Thank you. So, whatever I had just now explained, the same thing I have written here. So, see, this is a first I am using clear all and all, then parameter initialization, number of subcarriers, size of QAM or order of QAM, then signal to noise ratio, I had considered 0 to 30, then bitstream, same thing, whatever we have explained till now. So whole program we have written. Now simply we will run the program. So here first we are calculating the bit error rate. Now what I observed here, see in the command window, for this signal to noise ratio at 20 dB, the bit error rate we got as a 3.90 e to the power minus 5. So it is very, very small, 0.000039. So it's approximately equal to 0. So the SISO MIMO system is very efficient, we can say. And at all signal to noise ratio from 0 to 30, we are going to calculate. Just see this figure. In this we are going to plot the bit error rate versus the signal to noise ratio, and see the graph. as SNR goes on increasing, our bit error rate tries to decrease. So when the signal to noise ratio is good, what is signal to noise ratio? It is the ratio of signal power divided by noise power. So when the noise is less, the signal strength is more, of course the bit error rate will be less and it will go towards zero. So this is the second thing we are, second result we can say. First is the actual bit error rate. This is at 20 dB, and at all SNR values we can calculate. Then we can see the scatter plot. Just a minute, figure number 4 and this figure number 2. See, this scatter plot will give the constellation diagram of QAM. Now, as I told, what is QAM? Quadrature amplitude modulation. It is a combination of ASK and PSK. So here we are using 16 QAM, means 4 symbol, total 16 symbols. So see the constellation diagram of the 16 symbols. So the before transmission, these are the 16 symbols, QAM constellation. Then after receiving, these are all the bits which we have generated, and they are categorized into, or they are recognized as one of the symbol of the QAM. So when the signal to noise ratio is more, all these dots are very much nearer to the center point. If the noise is more, they are scattered away from the center point. So that's why using this constellation diagram, we can see the effect of the noise on the channel. So this is one more, we can say, the parameter to analyze the efficiency of our system. So using this constellation diagram also, we can see how efficient our MIMO, or sorry, this OFDM system is. So I hope you understood up to this. Please, please confirm. Anybody? Hello. Hello, ma'am. Can you see this?
Yes, yes, it is visible.
Yeah. So these are our received constellation diagrams, and this is our uh, signal to noise ratio versus the bit error rate. So here bit error rate is approximately 0 because SNR we have considered 20 dB. If SNR is less, you may get slight errors. So, but okay, normal SNR is almost from 5 to 15. Only in the rare case, the signal strength will be less. So, OFDM will give very good results in increasing the efficiency by reducing the bit error rate. So, this is a first thing, that is a single input, single output OFDM. Now we are going to implement the MIMO OFDM. Now, what is the use of MIMO? Because in our 4G and 5G systems, we are using the MIMO. MIMO is what? Multiple input, multiple output antenna. We are using the MIMO technology. So what is the advantage of MIMO technology? It is used to increase the channel capacity. It is used to increase the spectral efficiency. So just I'm going to this. Is it visible? Yes.
Yes, it is visible.
So now see why we are seeing, because we should know what is the basic OFDM. Now the same block we are implementing for MIMO. So once you understand that this will be easy for you. Here only two or three things extra we have added. So now we are going to implement the MIMO OFDM communication using MATLAB. So in MIMO OFDM, as I told, we have the multiple input and multiple output antennas along with the OFDM, which helps in boosting the data rates and the spectral efficiency. Again, it works by splitting. So what is the concept of OFDM? It works on splitting the high-speed data into the low-speed parallel streams, mapping onto the orthogonal carriers and transmitting through the multiple antennas. These multiple antennas helps in combating the fading effect and improving the spectral efficiency. We are using this MIMO in our 4G and 5G wireless communication. Now going through this block diagram of MIMO FDM. Now see, as I am telling, MIMO means what? Multiple input, multiple transmitter. So here, this is an example of 2 by 2 MIMO, two transmitter antennas, two MIMO antennas. Okay, two transmitter and receiving antennas. So for this we have the two streams. You can see the same block diagram is repeated two times, one for one transmitting antenna and second transmitting antenna. That's why we have seen initially single input. So this is the one part of SIO, this is one part of SISO. Combining it we will get for MIMO. Similarly, it can be, you can draw it for 4 by 4 MIMO, 8 by 8 MIMO, like that. So but before that, now, before going to this space-time encoder is a major concept in our MIMO FDM, which was not there in SISO. So, starting from again the data stream, we are using a modulation technique. First, you have to use a modulation or mapper. We are converting, or we are mapping the incoming bits to the number of symbols. If I am using QAM, 16 QAM, we are mapping to 16 number of symbols. Similarly, 64 or any QAM you can consider, or any other modulation technique also you can consider, like PSK, MSK, like that. Then, before implementing again OFDM, first we have to demultiplex using the space-time encoder. So, see the what are the key components in this process. Parallelly, we'll see. First is the transmission process. The data is encoded, then modulated and converted into the parallel streams. So, like this, the data is converted into the parallel streams. So, spatial mapping and MIMO coding. So, here to spatial mapping, depending on the number of antennas we are doing the mapping. Okay, the streams are mapped to the transmitting antennas. The different techniques used to to give the data for different number of transmitting antenna is STBC, space time block coding, or spatial multiplexing. It will increase the capacity. So as you are increasing the number of antennas, the capacity will increase. So accordingly, we are using the STBC for this, for the implementing this space time encoder. And then once it is given, once you are distributing over different antennas, then the process is same as we have done initially: serial to parallel conversion, then IFFT, then adding the cyclic prefix, again parallel to serial conversion. Okay, here only modulator. Here I had not described about the demodulator. Demodulation, OFDM demodulation will happen at the receiving antenna. Okay, this is only the modulator part. Okay, so this is the first, for first antenna it is given to the first antenna and then the second antenna. So this is the transmitter, OFDM MIMO transmitter block diagram. Okay, considering two antennas. And now we are going to implement this using the MATLAB. Okay, so as I told now, just first we are data encoding, then spatial mapping or MIMO coding, that is we are using the space time block coding or spatial multiplexing. Again, we are performing IFFT as we are doing the OFDM modulation. So IFFT, then we are adding the cyclic prefix to eliminate the intersymbol interference. Then now what, this is only the transmission side. What will happen at the receiver side? Now see, the data is coming from the multiple antennas, and at the receiving antennas also we have multiple receiving. So at any single receiving antenna, we have multiple copies of the incoming signal from the different antennas. So now we have to, initially there was only single transmitting antenna, single receiving antenna, but here there are multiple transmitting antenna, and if I'm considering single receiving antenna also, now we have the multiple copies of the input. So from that we have to receive the signal. So for that we have to do the channel estimation process. So in the receiving process, the signal passes through the channel shading. Once the signal is processed, okay, first we have to remove the cyclic prefix, then converting the FFT as we have done in OFDM demodulation block diagram. So removing the cyclic prefix, then applying FFT, converting back into frequency domain, and then performing the MIMO decoding and the for the multiple receiving antennas. So now channel estimation. Now channel estimation is very important here. Initially, the channel, there was only single transmitting antenna, single receiving antenna. So what was the relation? Y equal to simply Hx plus N. N is a noise at the receiver antenna, we can say. So here transmitting antenna but when it becomes 2 by 2 MIMO or 4 by 4 MIMO, the channel matrix size will be different. If it is 2 by 2, the channel matrix size will be 2 by 2. That is H11, H12, H21, H. So before receiving, so if you want to receive the data correctly, we should know this channel information. Once you know the channel behaving, then it will be easy to demodulate the signal without any interference. So the efficiency of your MIMO system based on the channel, how good the channel estimation is, that many errors will be reduced in the demodulation. So the channel estimation, how channel estimation is done. Channel estimation is done using different techniques. Pilot technique. So in that, known pilot signals are transmitted, and depending on the known pilots, the received these known pilots are known at the receiver, and using these known symbols and which are known to the receiver, we are going to estimate the channel coefficients. So we have the different methods such as zero forcing receiver, then minimum mean square receiver, then LS least square receiver, and so on. Okay, so that is the one of the important parts. See, channel estimation we have not done initially SISO, but in MIMO it is very important. So that's why this is one of the research topic in 5G or 4G or any communication, any higher generation communication. Channel estimation is very very important. Once you are doing the channel estimation correctly, demodulation, then reception, everything will be easy without any errors. Then what are the main advantages of this MIMO? MIMO system helps, we are using spatial multiplexing, multiple data streams which are transmitting simultaneously using multiple antennas, which are helpful to higher throughput. Throughput means you can write as a speed, so it gives a high speed. Then robustness, OFDM, as we know, it is very robust for the frequency selective fading, as well as it is helpful to reduce the intersymbol interference. Then efficiency, high spectral efficiency, and hence we are using in our 4G and 5G systems. This helps in reducing the complexity. So it will convert complex wideband channels by converting multiple complex into parallel simple channels. But again, as we know, each thing has its own advantages and disadvantages. So here the main disadvantage of MIMO FDM is the high peak to average noise ratio. Sorry, high peak to average power ratio. So we are trying to reduce it by using the linear high power amplifiers, as well as the computation complexity will be increased, because as the number of antenna increases, the channel matrix will, the size of channel matrix will be more, and hence it will be difficult to estimate the channel. So if there is small error in estimation the channel, then you will get a large bit error rate. So hence to get, so the complexity will increase as the number of antennas increases. So now we are again going to implement this block diagram, transmission as well as reception. This is only the transmitter part using MATLAB. Again, first thing is same. First we have to decide the number of transmitter antennas. So here I am considering NT equal to 2 number of transmitter antennas. Again, M equal to 16. This is a QAM order. Number of symbols we are considering. Again, first generate the number of bits. How many number of bits? Number of symbols, that is 64 into number of symbols, that is 6400 into 16. Okay, so here 4. So we are using the rand I. See, similar programs are mostly similar, only some changes as I'm introducing number of transmitting antennas. Initially it was 1, now it is 2. Then again we are using, again reshaping, we are converting into parallel, we are converting the data into symbols. How many symbols? 16 symbols, because I am using 16 QAM. So we are using reshape. Okay, reshape. Then we are converting bits to integer. Then we are using a QAM modulator. So we are using the QAM modulator. What is the size of QAM modulator? 16, as I am using the 16 QAM. And now we are, depending on the number of antennas we are transmitting, we are making into number of streams using again the reshape symbol. So now how many transmitting antennas? Two. So this whole we are converting again into two parts for two different antennas. Then again we are implementing OFDM modulation for each stream. Okay, so for each stream, I'm using the OFDM modulation. So OFDM modulation means again what? First, we are serial to parallel conversion equal to the number of subcarriers, then doing IFFT, then adding cyclic prefix, and then converting parallel to serial conversion. So see all these things we are doing here. So cyclic prefix 16 I'm considering. So first I'm generating a symbol matrix by reshaping. We are converting into lower streams. That is a concept of OFDM. How many symbols? As we have done 6400 something, and number of subcarriers we have taken 64. And here number of antennas, transmitting antennas are 2. Okay, so that dimension symbol matrix will be generated using IFFT function. We are going to take the inverse fast Fourier transform. Size of inverse fast Fourier transform equal to this. Then adding the cyclic prefix. So for C cyclic prefix, we are using again the for loop from one for both antennas. For both the signals coming from both antennas, we are using the cyclic prefix, and then again reshaping, converting the parallel to serial conversion. Now relay feeding. Now initially there was only single antenna, now there are the two antennas. So again we are using a flat relay channel. Now here how to generate a channel matrix. So what is the channel, what is the size of channel matrix? Here it is a 2 by 2. Okay, so we have to generate a 2 by 2 matrix. Now the each channel coefficient of this channel matrix is complex in nature. So size is what? NR 2 cross 2. So rand n is used to generate the random integer, random number. How many? 2 by 2 matrix. And again random plus I denotes the complex. Okay, so we are generating a channel matrix. So this H is a channel matrix. This is a channel matrix of size 2 by 2. Okay, then received signal. Now again received signal will be applying the channel. So what is the received signal? Y equal to H into X. Okay, so we are not considering any noise added at the receiver. We are not considering any EWGN noise. Here I am purely considering the channel interference or the noise added due to the channel coefficient. So what is the received signal? Received signal Y is equal to H into X. H is the channel coefficient matrix and X is a transmitted signal. So what is the received signal? Transmitted signal into H. Okay, and then okay, here we can add the next small n, that is the AWGN, additive white Gaussian noise. This is a noise added at the receiver. Then OFDM demodulation. Now once it is transmitted through the channel at the receiver end, we are going to reconstruct the original signal back. So theoretically, we have to remove the cyclic prefix, okay, and then taking the FFT. Now MIMO detection. Now as I told, first we need, so here we can use the different types of receiver, that is a zero forcing receiver or MMSC receiver. In zero forcing receiver, first we are estimating the channel using the formula H Hermitian H whole inverse H Hermitian. Hermitian is similar to the inverse, transpose of a complex matrix. We call it as a Hermitian. Okay, so this we are doing the channel estimation using this formula, that is H Hermitian H inverse H. So first we are doing the channel estimation. Once we have done the channel estimation, you can get the received signal by simply multiplying the incoming received signal with this estimated channel matrix. So in this for loop, we are calculating the received signal. See, what is our received signal? Received signal is the received symbols doing in, we are resizing equal to the number of antennas. Then we are multiplying this received signal Y with PINV. PINV means pseudo inverse matrix. This pseudo inverse matrix of H. What is H? H is a channel matrix. Okay, so how to calculate the pseudo inverse matrix? Actually, this is a built-in function in MATLAB, PINV, where this formula is automatically implemented. So pseudo inverse of H is equal to H Hermitian H whole inverse H Hermitian. So all this calculation is done automatically by using this function PINV, and this is the estimated channel. Once we know the estimated channel, by multiplying with the received signal, we are getting X hat. So what is this X hat? This is the estimated received signal. Okay, whatever we have transmitted the signal, this is the estimated received the signal. So this signal, we call it as a received signal or the received detected signal. In this way, we are first receiving the signal. Okay, so first what we are doing, first we are demodulating, we are doing the OFDM demodulation, and then we had used the zero forcing detection. Zero forcing detection, what it will do? It will multiply the received signal with a pseudo inverse matrix of H. H is a channel coefficient matrix which we have generated initially. Okay, so in this way we are getting the received signal. Okay, and once the received signal, now we are going to okay, so after this is at the receiving antenna. After getting the received signal at receiving antenna, what we are doing? Okay, after then we have to do the demodulation. Okay, so after detection, we have to do the demodulation. So again, I am using QAM demod. Again, this is a function, QAM demodulator function. We have to specify the M. We are using M equal to 16 for the received signal with a unit average power equal to 1. So we are doing the QAM demodulation. After getting the demodulated signal, we are converting that integers into the bits. Okay, so this DE to BI, that is a decimal to binary. So we are converting this decimal or integer bits into the binary symbols. Now we are going to, so these are our received bits. Now after getting the received bits, for our checking the efficiency of the system, we are calculating some parameters. Again, we are calculating the bit error rate. Again, what is the bit error rate? It is the difference between the transmitted bits and the received bits. Okay, so average. So here we are calculating the average error by adding whatever the bits not equal to the received bits. That many. So how many bits are there in error? We are calculating total number of bits by adding all those and dividing by total number of bits. So we will get the bit error rate. So bit error rate we are going to print. Similarly, we can print the QAM constellation to check the error occur or the effect of noise or the effect of the MIMO antenna on the performance. So these are the small blocks of the whole code, and then we are going to execute the code. Okay, I will just show you the code execution. So the same program which I explained just now, here the total program as it is, I had copied. So again, parameters, then my MoFDM simulation, then detection, and then same we are doing for different values of SNR. Now in this program, actually, I added the MMSC receiver also. Means I wanted to compare the two types of receiving, that is a zero forcing receiver and MMSC receiver. Actually, the disadvantage of zero force receiver is the MIMO, whatever the MIMO channel matrix, here we have considered 2 by 2. It should be a square matrix. If it is not a square matrix, we cannot use the zero forcing receiver. So that is the disadvantage, and hence we go for the another technique called as the MMSC. MMSC is the minimum mean square error. Again, it is having one formula depending on the correlation, and that is we can implement. So here we are going to compare the MIMO OFDM for the two different receiving, two different receptions, and we are going to plot the graph between the signal to noise ratio and the bit error rate. So just I want to run it. Now see here, in this diagram, here there are two graphs. One is for the ZF receiver and one is a MMSC receiver. Okay, at some one or two points we are getting these glitches. Otherwise, mostly we will get the similar graph. So here this is a graph for 2 by 2 MIMO FDM 16 QAM. So here the bit error rate is less as we are going for the higher SNR. Almost both are getting, if we change number of subcarriers or the signal to noise ratio or number of bits generation, high number of bits generation, slightly it may vary. Okay, so here uh, just a minute. This is a ZF same diagram we are getting. Now these are again the constellation diagram. So here in this, the bit error rate in this program, we obtain again 3.906 e to the power minus 5. E to the power minus 5 again means it is a 0.000039. So it is very, very small. So hence we are getting the received QAM constellation after ZF receiver similar to transmission. See, all the bits are very nearer to the center. They are not scattered away from the center of the each constellation points. This tells the bit error rate is small or the effect of noise is less. Okay. Similarly, we can do same program. We can extend for 4 by 4 MIMO or 8 by 4, 8 by 8 MIMO, which already I have done. And simply I want to, this is for, this is a comparison of 2 by 2 MIMO FDM and a 4 by 4 minor. Now here we can clearly see in 4 by 4 MIMO system, though bit error rate is slightly high compared to your 2 by 2 MIMO FDM, but it is a gradual reduce as well as you are getting a good channel efficiency. So theoretically, effect of 4 by 4 MIMO antenna is what? Capacity increases. So as the number of antenna you increases, capacity of channel automatically increases because the capacity is directly proportional to the minimum value of NT comma NR. NT is the transmitting number of transmitting antennas, number of receiving antennas. So hence in 5G communication system, we are using massive MIMO. In massive MIMO, large number of transmitting antennas. So automatically the capacity will increase. So hence 4 by 4 system can carry 4 parallel stream compared to your single. So hence automatically the capacity will increase with the help of MIMO. Similarly, large number of antennas, more antennas provides the less effect of the fading or stronger resilience against the fading. Okay, and if we are using a proper encoding, errors will drop significantly. But as I told, as the number of antenna increases, the channel estimation will become complex. Channel estimation is the very important point. Once the channel estimation is correct, then reception will be automatically correct. So but as number of antenna increases, the complexity increases. So channel estimation is harder. So there are different methods of channel estimation. Nowadays we can use the machine learning or deep learning technique also for channel estimation, which can perform its operation better. And in bit error rate performs same as so at the same SNR, the bit error rate improves if we compare 2 by 2 or 4 by 4. So using multiplexing, interference, bit error rate may slightly increase, but the throughput or the capacity is much higher. So this is a comparison of different sizes of the MIMO, 2 by 2 MIMO, 4 by 4 MIMO, 8 by 8 and 16 by 16. So as I told, okay, slightly the bit error rate values are more, but still we can use as the channel capacity increases with a very high value. So in 2 by 2, the bit error rate is good, but moderate diversity. As we go for higher values of MIMO, the bit error rate at high SNR is low, but computational complexity will increase. So hence we can say that increasing number of antennas provides the diversity gain as well as provides more capacity. Bit rate perform increases at higher SNR as well as complexity goes rapidly increase if you goes for higher values of your MIMO, number of transmitting antennas and receiving antennas. But different advanced detection techniques are there, not only ZF, MMSC, and iterative, so many other new advanced detection techniques, advanced channel estimation techniques, which are able to manage this complexity, and hence we can achieve a very high data rate and the channel capacity. So this is my last slide. So if you have any doubts in anything, you can ask. Anybody, please can ask any doubts regarding this. Hello, ma'am. Sujata, ma'am.
No, ma'am. Dear students, if you have any queries, you can unmute yourself, you can raise the questions, or else you can post your queries in the chat box.
I will give my PPT to ma'am so that they will forward to you. In that whole step-by-step MATLAB implementation of these codes are given. You can copy it and you can execute it and you can check. Ma'am, Subbarao sir is there. So he is going.
In 5 minutes, he is going to join. Meanwhile, we'll address some questions.
Okay, okay.
Because most of the students are from second year, no? They don't know.
Yes, because they presently they are studying analog and digital communication technique, and in this first mid they have covered only analog. They have not yet touched the digital technique.
Yeah.
So, but once the classes are going on, in that they will study about ASK, PSK, FSK, QPSK, QAM. Then they will be they will feel happy. Okay, we learned this already. We know this. So at that time you can do it. You can do these as a lab projects. This OFDM implementation as a lab project also you can do, because in lab we are doing all the basic digital modulation techniques, and that we can implement in MATLAB.
They have a doubt, Swapna. Can you give an
Yeah.
example for multi-path fading and intersymbol interference for better understanding?
Example means actually here in PPT are not included. We see when the data rate is very high compared to the bandwidth of the channel. If the bandwidth of the channel is big and the data rate is high, now see everything depends. See, if my gate is small and I am big, I am not able to pass through the gate. So the size of our, it should be less than the gate so that it will be easy to pass. So everything depends on the channel bandwidth and the data rate. So if the channel bandwidth is more, okay, so there will not be any intersymbol interference. But the channel bandwidth is less and the data rate is high. At that time, the consecutive symbols may overlap each other in time domain. That we call it as a intersymbol interference. This you will go. This already third year people may have studied. In second year, you are going to study in digital communication part. So up to, now I can tell up to this only, because again there are some derivations and all, some diagrams which will show the basically intersymbol interference means the overlapping of the consecutive symbols in time domain. If it is a square shape, it may fall gradually and it may overlap on the next coming symbol. We call it as a intersymbol interference. So what we do, we insert the cyclic prefix, means extra bits we are adding, so that though there is overlapping, it will not be the two consecutive bits. So hence this cyclic prefix will help to reduce the intersymbol interference in your OFD. Any other questions, please? See, all the programs, because as most people are students, I will suggest you to do implementation of whatever we are doing in analog and digital communication. Though it is analog communication, all the analog communication modulation techniques, AM, FM, PM, FDM, all the multiplexing techniques, as well as all the digital modulation techniques you implement using MATLAB, then you will get a very good command on this subject. Because mostly everywhere. In basically in communication, you should be very much strong at modulation techniques and the multiplexing techniques, because as the generation changes, the main change in this technology only multiplexing and modulation techniques. Any other topics to be discussed, please? Ma'am, shall we wait for 2 minutes so that sir will join?
Yeah. We'll wait. Meanwhile, anyone is having doubts, you can clear now.
See, on these topics, you can give your technical seminar also. Because in technical seminar, so many people are struggling to get the topic on which you are giving. So in communication domain, we have so many topics. One each, you can choose any one modulation technique, and you can give the technical seminar on that. That where it is used, how it is working, what are the applications, how it is implemented, the latest what are the latest modulation techniques and multiplication techniques, what are the applications, advantages. Each topic can be a one technical seminar topic, so it will be helpful for you.
Ma'am, can we get any project ideas related to this topic?
Actually, this project means these are you can do only a lab project, because not these are all standard things which already we are using. So it is not the new thing that we are generating something new using this. So like that you cannot do, but a project means you can do at a higher level, because already we have implemented 4G, 5G is already implemented and standardized. We cannot change, but we can do a small project. See, it depends on you are going to do a project at lab level or at final year level. If you want to do your project at final year level, you have to choose the advanced thing in 5G. So in 5G again, if I am going to select, okay, a massive MIMO antenna, then which type of modulation techniques can be used, what are the, then which type of multiplexing techniques can be used, then which type of different detection methods are used. So you can analyze those, you can do a comparison project, comparing all different methods, and which is the best for your, like that you can do. Or you can see nowadays the latest thing, you can use the machine learning or deep learning to do this process, because till in 5G also we are using the traditional methods only for this modulation, demodulation, then channel estimation, then signal detection. We are using the traditional methods, mathematical methods, but this can be implemented using machine learning. For that you need a data sets. Okay, data sets we don't have practically. So in site there are so many data types, data sets generated for 5G and 6G. You can use those data sets and you can implement the machine learning for doing these operations, for doing our basic wireless communication operations. This can be one of the research topic. This you can do for your as a final year project. Any other doubts?
There is a question, Sugna, how OFDMA and MIMO are interrelated. Both OFDM and OFDMA are for high speed and
Hmm.
have same applications. What is the difference between them?
OFDM are both same only. OFDM is what? Orthogonal frequency division multiple. See here, modulation, don't confuse in modulation and multiplexing. Okay, modulation means multiplexing means what? More than number of signals we are sending at a time. We call it as a multiplexing. In this, we are using orthogonal frequency division, multiple access. Multiple access multiplexing we can use as a synonym. And here the modulation technique we are using as a QAM, QPSK. That is a digital modulation technique. Okay, so here almost we can say QAM, that is OFDM, OFDMA are same. Ma'am, once you repeat the question, initial starting I didn't get.
How OFDMA and MIMO are
No,
interrelated?
no, see, OFDM you can do on single input, single transmitter, single receiver also. You can implement for large number of antennas also. So MIMO is depending on the number of transmitting and receiving antenna used. That can be anything. OFDM is the multiple access techniques. This is not depending on the number of transmitting an antenna, number of receiving antenna. It depends on how many number of frequency carriers you are using to transmit your data. If the data is more, you can use 64 carriers, 16 carriers, depending on that the OFDM. So to transmit, you can use OFDM to transmit over single antenna or multiple antenna. So it is not depending directly. You can use OFDM for any number of antennas. As per I got, I can tell this. Any other doubts?
Can you suggest any titles for final year projects?
Actually, so many are there. Once you visit to my cabin, I will give a list because here I don't have. So many things are there. See, as I told, main thing is channel estimation, channel detection, and then resource allocation. See, these are the broadly I am telling. Okay, resource allocation, channel estimation, channel signal detection. Okay, then in this there are so many algorithms. You can compare all the algorithms, you can do existing algorithm, you can analyze the existing algorithm, and you can improve the algorithm. And for all this you can go for the machine learning and deep learning techniques also. These are the topics for final year because these are the most advanced things which we can use for 5G and 6G communications.
Thank you, Swapna ma'am, for your elaborate explanation and clearing all the doubts whatever students raised here. And
Thank you very much, ma'am. I'm very thankful to you and HOD sir to give me
Thank
this
you, Madam
support.
Swapna, madam. Thank you.
so Bharat
Thank
has
you,
joined
sir.
just now. Sahasra? Yeah,
Madam.
Sir, 1 minute, sir, Bharat, sir.
ఓకే మేడం నా ఇంకా సెట్ చేయడానికి ఒక 2 minutes అవుతుంది.
Meanwhile, Sahasra will introduce you, sir. Swapna madam.
Yes, ma'am.
Huh. So
Yes, ma'am.
you stop sharing, madam. Thank you. Once
Okay,
again,
okay.
on behalf of EC department and all the students, participants, we are very much thankful to you for your time and clear explanation in what is the difference between single input, single output, and multiple input, multiple output six schemes. And that too, how we can apply this OFDM, what are the blocks, various blocks available in the way. Clearly you explained. For that, we are very thankful.
Thank you very much, ma'am. Thank you all.
Thank you, ma'am. Thank you for the great session. And now our resource person is our HOD, that is Dr. SPV Subhavrao, sir. It's a great privilege to introduce you, sir. A distinguished academician and a visionary leader in electronics and communication engineering. He earned his PhD in wireless communications from JNTU Hyderabad and brings over 2 decades of rich teaching and also research experience. He has made significant contributions in the areas of wireless communications, MIMO systems, and signal processing with numerous SIC indicated publications, books, patents, and also the funded research projects to his credit. Under his dynamic leadership, the department continues to achieve academic excellence and also research growth. It's my pleasure to invite you, sir.
Thank you.
Sir, it's your. Yeah, thank you.
Sir, please share your screen, sir.
మేడం అది చూస్తున్నాను. మొబైల్ నుంచి ఐ హావ్ లాగ్డ్ ఇన్ ది మొబైల్. ఐఎమ్ లాగింగ్ త్రూ సిస్టమ్.
PPT is also available in mobile, sir.
PPT is also there, but anyhow I'll log to my
Otherwise, you
laptop
can
and-
share it in WhatsApp. So I will open, I'll share from my end and I'll change and you'll explain, sir.
just I am opening, madam.
Okay, sir. I know.
Just 1 minute, madam. Okay, we'll start here. Just today, what I'll cover is 5G and what is the advantage of 5G. It is audible here, yes.
Yes, sir.
And how to implement some algorithms in 5G using MATLAB. That also I'll cover. మేడం హలో
సార్ చెప్పండి సార్.
ఈ పోస్ట్ ఎనేబుల్ చేయండి మేడం. ఎస్పీవికి
లేబుల్ ఉంది
చేయండి.
సార్ మీకు.
ఎస్పీవికి చేయండి.
ఓకే సార్, 1 minute.
డాక్టర్ ఎస్పీవికి చేయండి మేడం అది.
దానికే ఇచ్చాం సార్ కో-హోస్ట్.
షేర్ కావడం లేదు. నాకు హోస్ట్ డిసేబుల్ స్క్రీన్ షేరింగ్ వస్తుంది. 2 ఉన్నాయి మేడం నాది. డాక్టర్ ఎస్పి సుబ్బారావు, డాక్టర్ ఎస్పీవి.
1 minute, 1 minute, yes.
డాక్టర్ ఎస్పీకి ఇవ్వండి, షేర్ అవుతుంది స్క్రీన్.
Sir, now you try, sir. Sir, now you try to share the screen, sir.
ఓకే మేడం.
Okay.
షేరింగ్ మేడం అవైలబుల్. షేర్.
Not yet, sir.
మేడం వస్తుందా మేడం? ఓకే.
Yes, sir. Yes, sir. It is visible now.
Good evening all, and respected Dr. C.N. Sujata madam and Dr. T. Swapna madam. Good evening all my dear students. Today I will take the signal processing for 5G. Madam, it is audible?
Yes, sir. Yes, sir. It is clear.
That is clear, no? No echoes, no?
No echo, nothing, sir. Everything is clear. Screen is visible. Your voice is good.
Just I will give glance of this what is the important technologies in 5G, and also today what I want to cover is just briefly I will explain what is 5G and what are the important technologies we are using in 5G, and how to implement that some algorithms in 5G also, that I will cover here. So first is you know here 1G, 4G. 1G we are using, that is the example of 1G is AMPS, Nordic Mobile Telephone System, and telephone TACS, and we are using here analog. They are examples of analog cellular. In 5G we are having here DMPS, that is digital analog digital advanced mobile phone service, GSM global system for mobile, and GPRS. In 2G we are transmitting voice in terms of digital, and the data rate is in terms of around kilobits, around 114 or 122 kilobits. In 3G we have CDMA, code division multiple access, 2000 WCDMA wideband code division multiple access, and that is developed under 3 generation 3 GPP. Here it is optimized for video transmission. In 3G onwards you can transmit video. In 2G we are not able to transmit video. Okay, and the data rate in 3G is it is going up to 2 Mbps. Next in 4G we have long-term evolution, and it is having a maximum data capacity. You are getting under the data range is in terms of the data rate is in terms of 100 megabits per second here. So you refer here. Here these an 1G communication. Here we are transmitting only analog. In 2G we are transmitting digital voice, as well as we are transmitting only data. The data rate is less than 0.5 Mbps. In 3G we have the WCDMA we are having here more bandwidth than CDMA, and you can transmit up to 63 Mbps. It is optimized for video transmission and also multimedia transmission. In mobile 4G, we are having a data rate 300 Mbps. So as we are increasing the technology, what we are having is the data rate is getting increased. Now, when you are going for 5G technologies, here the main important feature of 5G technology is the bandwidth is hundreds of megabits per second bandwidth, and the latency. Here latency is delay between node to node. The latency is less than 1 millisecond, and the throughput is greater than 30 Gbps, 30 gigabits per second. We can connect more than 1 million devices. So that is the advantage of 5G. You can have massive broadband. Suppose any user want to have bandwidth of 1 gigabit per second, 1 gigabit, more than 1 gigabit, the technology can able to provide, a service able to can provide. So that is bandwidth on demand. So these are the important revolutions taken in wireless communication technology, that is in 5G here. Latency is less than 1 millisecond, means that is very good here. Delay is very less than 1 millisecond. You can transmit data very fastly here. Okay, we can connect more than 1 million devices at a time. That is the advantage of 5G here. Now, it is 5G is impact in every industry here. Okay, if you go for the medical, you go for multimedia, you go for education, you go for industry, okay, in all the, in hospitals, in transport, in data logistics, in all the fields, the 5G is impacting in all the lives here. Okay, and the Internet of Things plus 5G is what we are calling as next wave of connectedness. Okay, these two are, okay, 5G plus Internet of Things. We are the backbone, and it is enabling the industrial revolution. Okay, these with this so many applicants we are able to do now. Okay, now what is the advantage of 5G is we can increase the data rate 1000 times than 4G. We can connect devices 10 to 100 times, and we can improve the latency is improved 5 times. End user data rates, they are improved to 100 times, and the battery life is improved 10 times. So we are when you have seen all the mobiles at the earlier, we are having here the mobile is of brick size, and now we are getting very small size mobiles. The weight also very less, the power dissipate, the battery power also very improving, and we are having here more features, and we are increasing the data rate also here. Okay, here 5G technology, it is used in all the fields here. In precision agriculture, we are using. In autonomous vehicles, we are using. In drone delivery, we are using. Okay, in real-time shipping, we are using. In smart logistics, we are using. Autonomous driving and commerce applications. Okay, and in space also, in space technologies also, we are using here is 5G technology here. In vehicular communication also, we are using now 5G technology here. Okay, the massive sensor network here especially it is used for precision agriculture. Okay, we are having here sensors, different sensors are there. We can cultivate large amount of land. They are connected to the network. Through the network, we can give instructions to drone, and we can do precision agriculture here. And these wireless IoT transport hubs, okay, we can use in vehicular communication here, especially when you are going for autonomous vehicle. You will give your directions here where the the private networks are there, where is the network, where the hospitals are there. All the instructions will be seen in the given to the autonomous vehicle, so that it will take as per the instructions. The future autonomous vehicle. This is the future autonomous vehicle. Also we are using here. This is the logistics, and when you are going for virtual reality, okay, no need to go to shop and wear dress. and see here whether it is fit or not. You can see from your home here, and you can see, and you can order also. That is also possible virtual reality applications. Okay, next is in industrial evolution also we are having here. So, and so many applicants are there for 5G here. Now, here future digital economy we are getting through communication is $12.3 trillion. That is the advantage of wireless communication. Any country, if you refer here, more telecom sector, they are getting more revenue here. Okay, nowadays, earlier we are not using more, earlier days, most of the human beings, they are not using the mobile phones. Now it is without mobile phone, no human being can survive. Like that scenario came, and because of this, the telecom sector is having more. It is great. It is having good future digital. It is powering the future of digital economy here. Okay, now the LTE long term evolution, that is 4G, that we are going for 5G applications here. Here, if you refer this diagram, we have here 5G NR millimeter wave. That is here the data rate is up to 10 gigabits. It can cover only small area. Here you can have the data rate up to 10 gigabits. And if you refer outer cell, is we are having here 5G NR. We are using a 6 GHz band. Here and we are using here 4G LTE coverage. We can have the bandwidth. You can have the data rate of 1 gigabyte. And if you go outside circle, we have LTE. We can have volt. We can have data rate in terms of 100 megabits per. We can have data rates in terms of 100 megabits. So here, yeah, we are using here. We are using different scenarios here. Here, for smaller cell, we can have one data rate. For medium cell, we can have one data rate. For longer cell, we have one data rate here. Now we'll see what are the 5G technologies. They are the 5G technologies. They are the 10 pillars of 5G. One is radio access technology, and we have self-organizing network, SON, that is what we are calling as SON. Next is millimetric wave, that is operating at 60 gigahertz. We have energy efficiency network, RAN, radio access network, machine type communication, broad backhaul network, and spectral efficiency. They are the 10 pillars of 5G. We will discuss some technologies here. So finally, when compared to previous generations of wireless technologies, the 5G will give 10 times the improvement in the data rate, 3 times improvement in the spectrum efficiency. A spectrum efficiency means how efficiently you are utilizing the frequency spectrum. Spectrum is very important resource in communication, and if you are, and it is also mostly a value, mostly most costly resource. And if you are not utilizing the spectrum efficiently, you can't provide more number of users. When you are providing more number of users and you want to provide excellent service, quality of service, you have to efficiently manage the frequency spectrum. So we are having a different techniques are there for efficiently managing frequency spectrum. Here it is giving a 3 times the existing wireless technology here, and we are improving 10 times the latency and 100 times the network energy efficiency here. These are the next is the 3 high levels of 5G users. Okay, here we are enhancing the mobile broadband. Here earlier we are having a data rate of 100 megabits per second. Now we are going up to 10 gigabits per second using 5G here. You can have machine, massive machine type communication. We can connect to IoT devices. We can connect so many. We can connect up to millions of devices to the network, and we can connect. We can control. So we have massive machine type communication, and we have ultra reliability and low latency also here. We can here we can have less delay between source to destination. So these are the main stages here. Enhance. These are the 3 levels of any 5G communication, enhanced mobile broadband, massive machine type communication, and low latency communication here. Okay, here what is ultra low latency? Here, if you are transmitting packets in a computer network, okay, the computer network is optimized to process very high volume of data packets with low delay. That's what you are calling as ultra latency. Low latency measured in terms of hundreds of nanoseconds here. Okay, here it is 1 millisecond is qualified as ultra low here. Here only here we are transmitting data in terms of packets. What is packet is your large data is divided into smaller pieces, and we are adding source address, we are adding destination address, we are adding a packet sequence number, and we are adding error control mechanism that forms a packet. Here the packets are transmitted on the network. The different packets will transmit different directions, different paths, and reach destination. At destination, you are reordering the packets. Now, when you are opening some site, we may not get immediately, the site is not get open. What is the reason is the packets related to the site are not received. Once you receive the packets, then it is open here. So here the low latency is measured in hundreds of nanoseconds with under 1 milli with one. Okay, under under 1 millisecond means it is qualified as ultra low. See, that is a delay. 1 millisecond is the delay. Next is machine to machine communication. Okay, we are using artificial intelligence and machine learning algorithms without manual assistance of humans. We can able to control the network. We can transmit the information and perform actions. Okay, the machine to machine communication. And enhanced mobile broadband. This is what you are calling as EMBB. It will enable new data-driven experience here, especially when you are going virtual reality and augmented reality. This mobile broadband require here more. You require here more bandwidth here for this application. This 5G, it will supporting this application. You require more data rate, that will be faster. Okay. So this is provided by 5G technologies. Okay, now they are the innovative wireless technologies for 5G here. What are the innovative technologies for 5G are? One is massive MIMO. Massive MIMO. Already just now Madam has covered what is the MIMO here. Multiple input and multiple output. Massive means here you are connecting large number of inputs and outputs here. The large number of antennas we are using here, nearly 200 to 300 antennas we are connecting, okay, to a network, to a node. It will provide high multiplexing gain, it will transmit more data here, okay, it will, it reduce the radiated power. And millimeter wave technology, another is millimeter wave technology. Here we are using millimeter wave frequency band for 5G applications. So that is called as millimeter wave technology. What is the millimeter wave technology? Is 30 gigahertz to 300 gigahertz. This is the millimeter wave band. This technology, it provides higher throughput in small geographical areas here. Okay, you want to have more, want transmit more data rate. What you do is you have to go for smaller cell area here. You can get high throughput. Next is full duplex radio technology. Full duplex radio technology. Now, what is this full duplex radio technology? Is here we can duplex. Duplex means we can two sides, in two directions we can transmit the data. Full duplex means simultaneously transmission and reception of data will take place at the same time in the same frequency band. This is the full duplex radio technology. This is not, okay, in 5G only we are having this full duplex radio technology. So because of this, we are improving the spectrum efficiency here. In other, we have 4G, we are not having full duplex. We can transmit in both directions, not at the same time, but it is possible here. Next is a filter bank multi-carrier. This is also one of the technology we are using. Here, here we are using OF, similar to OFDM. Here we are using multi-carrier transmission, multi-carriers. We are, okay, when you are using multi-carriers, there will be interference. So what you are doing is we are using here sharp filters, so that the data will not be, there will be no crosstalk. We can easily filter the noise crosstalk. So we are using a multi-filter bank for multi-carriers. So that is called as filter bank multi-carrier. This is also one of the applications. These all one, each one is one research topic. MIMO, millimeter wave technology, full duplex radio technology, and filter bank multi-carrier. Next is the also non-orthogonal multiple access, NOMA. This what you are calling as NOMA. Here we are using multi-users. Here multi-users are transmitting on the downlink and uplink. We are using here at the same time, at the same code, we are using same code, same frequency, but with different power levels. Okay, this is one of the new concept here. Your users are separated with different power levels here. Especially this NOMA will be used in IoT applications. Okay, when you are going for IoT applications. Next is cognitive radio. In cognitive radio, here it is, we can see the frequency spectrum, unlicensed, unused frequency spectrum. The unused frequency spectrum can be shared to secondary users, so that we can, again, we can provide, we can improve the spectrum efficiency here. Next is cooperative communication. Cooperative communication is we are using one or more relays to transmit the data here, okay, to the destination. This is the cooperative communication. Now, present scenario, how we are transferring data from mobile here. Okay, we are transferring data from mobile to base station to base station controller, then MTSO, mobile telephone switching office, then to the network, and then base station controller to the other to the destination user, and base station again to the destination. Now here with relays, we can, your mobile at as a relay, through your mobile you can transmit your data to your friend. Okay, that is the cooperative communication. Okay, this is the MIMO block diagram here. Here at the base station, here at the mobile also here. Here mobile also, just now we have only one receiving antenna, but you can have an array of antennas in 5G here. Okay, that also you can see that also arrays of antennas also possible. Will be there in 5G mobile. Okay, this is the block diagram of MIMO diagram here. Here we are transmitting data. Here whatever the data that we are transmitting, that is converted into bits. You are transmitting voice, you are transmitting video, you are transmitting image, that will be converted into bits. You are doing coding, you are using source coding, channel coding, and then you are going for modulation, digital modulation. Here all these antennas, they are connected to weights. We are adjusting the weights, that changing weights such that there will be no interference. Okay, this is the MIMO block diagram. Madam has covered. I am not detailedly discussing. And this is the millimeter wave communication. Millimeter wave communication, we have in this here in this we have just line of sight communication. Here especially this millimeter wave communication is useful to operate in small geographical areas. We can't operate more area, more larger geographical area. Okay, that also tell why, what is the region here, that will be discussed here. Okay, next is here we are using backhaul portion of the network. Okay, suppose what is this backhaul portion is, suppose a link is broken between two nodes, we can have another intermediate link to connect that nodes. So that is backhaul portion. That is okay. That is also there in 5G here. Okay. Next is beam forming. We are using here multiple antennas, and we are controlling the direction of the wavefront by varying the weights of the individual by varying the magnitude and phase of the antenna signals. So this is called as beam forming here. Here This here, the tower, we are having here multiple antennas, and we are varying the weights of the antennas, gain of the antennas, such that the wavefront can be changed. We can transmit in a particular direction. This is a beam direction. This is what we are calling as beam forming. By using beam forming, we can reduce the interference. We can transmit data in a particular direction so that we can reduce the interference from other users. So this is the beam forming technique we are using. Next is the spectral bands. What are the spectral bands we are using here? For wireless communication, we are using 300 megahertz to 3 gigahertz. The wireless communication, for wireless communication, we are using this, what we are calling as sweet spot or beachfront spectrum here. Okay, but we can't transmit for longer distance here. Okay, this band. So for that, and we want to increase the data rate. This spectrum is limited because we can't increase the data rate for wireless communication. So what we are doing is we are using millimeter wave band. These millimeter wave band were used for radar applications, airport and air traffic control communications, and as well as IEEE wireless personal area network, that is IEEE 802.15.3c and IEEE wireless local area network. So we are using that band. What is the frequency band we are using is 3 GHz to 300 GHz. 3 GHz to 300 GHz. That is the millimeter wave band. In 3 GHz, here 54 GHz, here 54 GHz we are using for this wireless 5G communication from 57 to 64. 57 to 64 we are not using here. This band is oxygen absorption band. Because of presence of oxygen molecules, the signal will be observed. Next, after that, we have 99 gigahertz. The 99 gigahertz we are using here. From 99 gigahertz we are using, and from 164 to 200 gigahertz we are not using. Because of presence of water vapor molecules, that will be observed. Next, after that, we have 99 gigahertz. So if we add these 3 gigahertz and these, so what are the frequency bands we are having here? We are having here is 54 gigahertz and plus 99 gigahertz plus 99 gigahertz. Total we are having a 252 gigahertz bandwidth available. 256 gigahertz band. So much bandwidth available for 5G communication. Here this particular band 57 to 64 and 164 to 200 we are not using for this wireless 5G communication. This frequency band 57 to 64 and 164 to gigahertz is not suitable because of presence of oxygen water molecules here. And here the oxygen absorption, the water vapor absorption here. Total bandwidth available is 54 plus 99 plus 250 gigahertz. And what are the millimeter wave challenges? Because of high carrier frequency, propagation loss is more, and your penetration loss also more. When you are transmitting signal to a glass, the loss is of 40.1 decibels. When the signal is transmitted on a brick pillar, the loss is of 28.3 decibels. When you are transmitting the signal in indoor materials, okay, we are getting a loss of non-tilted glass. It is giving a loss of minus 3.6. Dry walls, we are getting a loss of 6.8. Even humans also creating a loss for this millimeter wave communication. It is very sensitive blockage by obstacles such as humans and furniture. So it is having a weak diffraction ability. That is the problem. Another problem is okay, you have transmit your signal in only a particular direction. Otherwise, you can have more interference from other users. So one is here one of the main key factor is MAC design, medium access control design, and here to another important factor is how to improve the network capacity by using your frequency use. They are the challenges. Other challenges are we are using your integrated circuits and system. We are using your power amplifiers, and they are causing nonlinear distortion. We are getting phase noise, and this we are using your in phase and quadrature phase components especially when you are going for digital modulation. These in phase component, quadrature component are in balance. We are using a large antenna arrays. Okay, here when you are going for a large number of antennas, these antennas are operating at radio frequency, and yeah, especially required some signal processing techniques. So they are the challenges lying here in this year. Okay, now already these have covered here. Here channel estimation is challenging in MIM. Channel estimation. Here we are using a TDD and FDD technique here. TDD means here time division duplex, and FDD is frequency duplex. Here when you are going for conventional communication, it applies soft duplex mode. Duplex, but when you are transmitting, others will, okay, off duplex mode. Now we are using frequency division duplex. What is frequency division duplex is, here for uplink we are using one frequency band, and for downlink one frequency band. These uplink band and downlink band, they are separated each other. This what you are calling as frequency division duplex. Next is time division duplex means we are using same frequency band for uplink as well as downlink. The frequency band will be shared on time division, time scale. This is the time division duplex. Okay, we are using both FDD, TDD. We are using full duplex radio technology. Okay, they are the thing here. Okay, here what is the main advantage of this TDD is God time intervals. What is the advantage of this FD? What is the advantage of this FD is here when you are covering here when you are working in FDD mode, frequency division duplexing mode, there is a gap between uplink frequency and downlink frequency. The gap what you are calling as God band. So that God band, here extra frequency band we are using for this God frequency band. Okay, we are not efficiently utilizing the frequency spectrum. Okay, but in frequency in full duplex, there is no need of God band, so we can improve the spectral efficiency. So what are the challenges in full duplex? Okay, simultaneous transmission of uplink and downlink, it results in self-interference. So the self-interference can be suppressed at physical layer for improving the performance. This is also one of the research topic here. How to reduce the self-interference in full duplex. Next is this also a filter bank multi-carrier. This is also one of the important topic here. Here we are the filters. Here we are using a enhancement over a OFDM here. A OFDM, we are using a orthogonally spaced carriers. Here we refer here, we have the sync pulse. Here we have main pulse and main lobe and side lobes. Here the main lobe will carry actual information. Main lobe will carry most of the information. The side lobes, what you are doing is, the side lobes are interfacing with other main lobes and causing interference. So here what we are doing is, here for to separate these side lobes, we are using a filter bank so that it will reduce the interference. So we are using your filter bank multi-carrier. Okay, these side lobes are filtered through this filter bank. So we are using your filter bank multi-carrier. Okay. So yeah, these are the OFDM MetaMask code. I am not covering here this OFDM and all this. So these are the 5G technologies we are having here. And next is a non-orthogonal multiple axis here. Just I'll cover what is non-orthogonal multiple axis. Now you refer here the diagram of non-orthogonal multiple axis. User 1 is near to the, you are having two users, user 1 and user 2. What is the principle of NOMA is, user 1, you are having here user 1 and user 2. User, okay, both are operating at same time at the same code, using same code and same frequency here. But what is the difference here? The difference is power level. If you refer here user 1 is having more, okay, user 1 is closer to the user 1 is closer to the base station, so it receiving more power, and user 2 is, okay, away from the base station. You are not reaching that much power here. Okay, so now how we are okay, user 2, when the signal is received user 2, directly we are decoding the signal. When you are receiving the user 1, what we are doing is, when the signal is received at user 1, we are subtracting user 2 signals from user 1. Then that is what we are calling user 1 signal decoding. This is what is called as SIC. SIC nothing but here successive intersymbol interference. Okay, SIC, successful interference cancellation. Okay, user 1 has, here user 1 is having higher channel gain when compared to user 2. It is receiving more power than user 2. So here you are getting interference from user 2 also here. So what you are doing is user 2 power is subtracted from user 1. This is successful interference cancellation. Okay, how your NOMA work on power. Now you compare NOMA with OFDM. NOMA with OFDM, what is the difference is the difference. Here user 1, now in this case you refer here, user 1 is there. User 1 is closer to the base station, it is receiving more power. User 2 is far away from the base station, receiving less power. Now here the power levels are different. For user 1, it is one power level, high power level. User 2, there is a low power level. Okay. Now here, if you refer here OFDMA, the power levels are same. For user 1, there is one power level. Same power level for user 2, but there are difference in frequency here. Okay. So here, what is the difference between OFDM and NOMA is, here user 1, for user 1, we are receiving signals from user 1 as well as user 2 with high power. But when you are going for user 2, we are receiving signals from user 1 as well as user 2 with less power. This is in OFDMA. But when you are going for NOMA here, when user 1 is near to the base station, you also receive signal from the user 2 also. So what we are doing is, we are subtracting user 2 signal and we are decoding. Okay, this is the concept of here NOMA here. This is also one of the good research topic here. Now this is the architecture of 5G networks here. Here this architecture, we are having here mobile base station. Here can have direct communication. You can directly connect to your mobile base station. And mobile to mobile devices are communicated. Now you see here DC to DC. Mobile to mobile devices are communicated and they are connected to mobile station. And your mobile device can act as relay. You can connect to your friend mobile and then connect to the base station. And so, you are having different techniques here, different methods for connecting your to the network here. Okay, just we'll see the device control here. Here, this is a source station, the source mobile. This is the other mobile. This other mobile is acting as a relay. We can connect source to relay, then communicate to base station, or you can directly communicate to base station. This device is relay operator. Next is, another thing is the source and destination can be connected directly without, but they are under control of base station. Direct to direct link is possible here. In this, there is one advantage here. And next is, you want to connect source to destination. There is no base station. You can connect to your mobile friend. You can connect to other mobile that is acting as a relay. You can connect to other mobile that is acting as relay. Through relay, you can transmit data source to destination. The device relaying with device control. They are the technique. Without base station, you can directly communicate source to destination. That is another advantage. They are the techniques you are using it. Now, when you go for 5G networks, you have open here, having your open access network here. We are having your physical layer, data link layer. We are in 4G, we are having your total. If you refer any OS reference model, you have total 7 layers: physical layer, data link layer, network, transport, section, presentation. When you are going for 5G, this data link and physical layer called as open wireless access network. This network layer is divided into two types: upper network and lower network. And this open transport layer, that is presentation, section, and transport. These comes and open transport. They are the next application layer. This is the architecture here. You can, they are the advantages of 5G. Data bandwidth of 1 gigabits. It is available at cost. Quality of service. Quality of service very important. Call blocking is very important. Call dropping is very important here. Yes. They are the, what is the disadvantage? It is operating at high frequencies. Here are blocking by buildings and you can't cover long distance. So we are using a different for long For smaller distance, we are using high frequency. For medium distance, we are using one frequency. For longer distance, we are using frequency. See, okay, there are 5 applications. We are using 5 phones. Now this is about your 5G here, and we are the others. Other okay. The next is 6G. Now here, what is 6G here? 6G is we can go data rate more than 100 gigabits per second. Here it is 100 times 100 times capacity. It provides 100 times capacity here, and we can get gigabits coverage everywhere. Here we are not getting gigabits coverage. Only smaller cell only we are getting. In 6G we can get gigabits coverage here. Now we can coverage areas also. It is new coverage also sky. That is more than 10,000 meters in sea, 2,000 nanometer in space also we can get. Okay, we can have extremely low energy and cost. We can have millimeter wave. Here we are using terahertz frequency band. Okay, here device is free from battery charging. We are the other thing, and latency is less than 1 millisecond, and we can have guaranteed quality of service. Okay, and we can have more massive connectivity devices and high precision position. Okay, we can get precision positioning of order centimeter order. We can connect 10 million device per square meter. These are the requirements for 5G here. Okay, you can see here later 6G here, and this is my thing here. And next is just I'll give one how you can have wireless communication ramp here. Wireless communication ramp that also can do wireless communication. That I will show that also. That just I will not take more than 5 minutes or this. Just I will show this. There is a 5 development using MATLAB. Okay. Okay, this is 5G development using MATLAB. Here I am here. Here this book will be shared to you. Here what are the technology and design, what are the new architecture algorithms, okay, technology design, how can go, what is 5G, given applicants, what is driving 5G, okay, what are specifications of 5G here, energy efficiency is greater than 90%, throughput is greater than. Where some applicants have given here, how to analyze the physical layer for 5G. Okay, this again how to analyze physical layer. Okay, what you are doing in physical layer, you are using especially this modulation technique, coding schemes. We are using source coding technique, okay, and modulation digital modulation technique, and beam forming, and all this we are doing at physical layer here. Okay, converting of your bits to signal for transmitting. This we are done. These are doing at physical layer. You can do some programming. Okay, at this in this. Next is a millimeter wave high air frequency here. Here when you are transmitting, we can transmit data rate from 1 gigabits per second to 50 gigabits per second. How can you transmit? Okay, what we can do? Yes, coding in this millimeter wave communication that also available. Massive MIMO antennas here. This is here massive MIMO antenna. Here this is for especially you are using here 5G applications here. Here we can you can simulate this antenna. We can have antenna coupling hybrid beam forming. Okay, we can have Marcy MO antennas. You can change the gains of the antenna. You can see what is the spectral efficiency. You can see it. And these are test bits also there. You can verify the test bit also here. You can, for still more material, you can refer design 5G wireless communication with this MATLAB simulating. So many resources are available, videos are available on 5G MATLAB. And when you want to develop new architecture algorithms also, you can see here. Okay, we can have Simulink also here. Okay, when you want to see the transmitter receiver, suppose you are developing algorithm for beam farming and you are developing algorithm for interference, power control, you can do here. On physical layer also, we can improve the algorithms physical layer for improving spectrum efficiency, for power control, call admission control. All these are available here. Okay, for channel models here, for channel coding, all these are available here. You can see these MIMO arrays here. MIMO arrays, and MIMO also can work here. Okay, all these things are available in 5G toolbox. Whatever I am showing, these antennas here, these are available in your toolbox with examples. Can see that also here. Okay, next is power amplifier. You want to work on power amplifier for 5G, you can use Simulink and can work here. And prototypes you want here, so can work on this also here. Okay, these I will share to you here. And OFDM modulator, this when you want to implement ADL implementation on FPGA and ASIC code, you can download MATLAB code on FPGA also here. That also possible. Okay, this is one thing. I will share this. Another thing is you register. Okay, just I'll. You go for Google, yes, and what you do is just you write here online MATLAB online RAM, MATLAB online RAM. Okay, yeah, getting yes. And what you write, that matter. Okay, and matter. So it's just just I hope, but you can come. Always, what you do is net law. Just a net is law. Net law.
guys?
Hello.
Yes, sir. You can share now.
Just actually, we have MATLAB online ramp. In that, it is a self-face. You can my laptop is disconnected with net. So if I am getting, I'll show. Otherwise, what you do is, uh, you can try that. It is self-face. Here, so many online ramps are there. In that, we have machine learning online ramp, wireless communication online ramp. Get a selfie that will explain, as well as it give task also here. You can complete the task. You can it will explain the code. It will give the result, and it will explain the syntax. And after that, it will give task. You can do the task. Even if you are not doing correct, also it will give the solution, and you can get the result also here. You can do that online RAM after completing that wireless communication or any so many online RAMs are there available. If you complete that, you will get a certificate from MATLAB, MathWorks. That will be useful for you also. You can try that also here. If I'm okay, yes, there is a thing I want to share. There is the okay, madam. This is from my side. There is the now I got madam. Okay, madam. Just okay. Hello, madam. Okay, and that and because of network problem, that I will share that document to you. You can see that. I will share this online RAM document wireless communication to you. You can complete it and you can get the certificate here. Because of this network problem, I'm not able to show on the online here. Okay. Okay. Yes, sir. Thank you for all of you. Okay. Whatever the material I have shared, printed, I will be shared to you. You can work in this area. Okay. You can.
Okay, sir.
Thank you, madam. Thank you. This wireless communication online RAM, I'll share, madam, and also this PPT and this MATLAB, whatever PDF you have
Okay,
shared,
sir.
no,
I'll share in
that
the
I'll share to you.
WhatsApp group, sir.
That is the okay. I'll share so that they can complete that online ramp. They can get certificate here. So many are there in that. They can complete that. They will give that much certificate. If you complete machine learning online ramp, they will get certificate. If you complete signal processing online ramp, they will get certificate. You can
Okay,
do
sir.
that. Wireless communication ramp, I will share the document. The pro. Okay.
Okay, sir.
That
Thank
is
you, sir,
helpful.
for your insightful and engaging session on 5G signal processing technologies. Your explanation of 5G concepts, including modern signal processing techniques, challenges, and research directions, has greatly enriched the understanding of all the participants. Once again, thank you very much, sir, for your enlightening session, for contributing to the success of this workshop. Thank you very much.
Thank you. Thank you all. Thank you. Thank you.
Thank you, dear students. Good night. I know that we extended a little bit time, not little bit, half an hour almost. Thank you for your patience and thanks.
Thank you for students.
Okay, sir. We can leave for today.